Quick run through kinetics. I'm not going to go through all the bits and pieces, just the key ideas of the maximum Boltzmann distribution. Remember that the y-axis is number of particles, not frequency, thanks. And then the energy of each particle is along the bottom there.
No energy, no particle can have no energy.
Zero particles have zero energy, thank you. So the graph always starts at the origin, goes up, and then comes down and levels off. That's one of the worst maximum Boltzmann distributions I've ever drawn, so let's just draw that again with a bit more nice curviness. That's fine. Remember that the average energy of the particles is always slightly to the right. And remember, it's on the energy axis. So the peak, the number of particles with the most energy is the most common energy found for particles would be here. The number of particles with the most common energy would be here. And then the average energy is always just slightly to the right of that peak. If we increase the temperature of the gas, what happens to the graph? We increase the temperature, shifts to the
right.
and the peak
Is lower.
is lower. Okay, so something like that.
And more activation energy. Like the area
More particles have
Come to that in a moment.
or higher.
So at a higher temperature, the graph shifts to the right and drops a bit. That's because the area under the graph remains constant. What's the area under the graph represent?
The number of particles.
Let's see how many colours I can get into this. Yeah.
particles.
Well done.
Area under the curve represents the total number of particles, or particles. There we go. So if I increase the temperature of the gas, of course, I've still got the same number of particles, unless it's reacting. Let's not go there. So the area remains constant. So then I heard a couple of people saying, yeah, if we've got an activation energy on our graph, and we increase temperature,
What's the question?
yeah. Why does the rate of reaction increase if we increase temperature using?
More particles have energy.
Can you put a word in front of more for us? What he said? Many more. Many more. Many more particles have energy greater than or equal to the activation energy, which is easier to express in symbols. Many more particles. Don't forget the word many. That came up in the 2022 exam, and the word many was specified in the mark scheme. Many more particles have energy greater than or equal to the activation energy. In other words, when they collide, those collisions will be successful, to put it in sort of GCSE terms. Of course, we know that if you add a catalyst, that drops the activation energy, so then of course more particles will have that energy, and it does that by producing an alternative pathway for the reaction, the lower activation energy. And then the usual kind of things apply. If we have higher pressure, the rate goes up because GCSE answers still apply. Increase in pressure, rate goes up because
More particles in a smaller area.
more particles in the same volume. Can we go for? Yeah.
Frequent.
What comes before that?
More
Don't forget the F word.
frequency.
Yeah. So higher collision frequency, please. Not just more successful collisions. Higher collision frequency or more collisions per second. That's what frequency means. And surface area, you know, that still applies. Higher concentration, that still applies, etc., etc. Okay. So then we spent quite a lot of time on equilibria. Again, all the Le Chatelier content. Still applies. So the key idea of Le Chatelier's principle.
Any change is
The equilibrium
met by an
shifts
equal contraction.
The equilibrium shifts to minimize the change.
Minimizing the change. Yeah, that's what you take into the exam. I mean, if you're asked for a definition of Le Chatelier's principle, you'll have to write that down. The equilibrium shifts to minimize any change.
Song.
And there's a song about that, we know, don't we, children? But the words minimize the change are not the answer to every question about equilibrium conditions, okay? The words minimize the change need to be in your head, but given a question about increasing a temperature, and let's go to our old favourite, the Haber process, covered much in GCSE. So given an equilibrium like the Haber process with a delta H value, we can say increase in temperature will
Shift the equilibrium to the left.
shift, yeah, so we either talk about, we can say shifts the equilibrium position
The end of length.
to the left, that's fine because that's the endothermic direction. Or we can say, talk about yield,
The yield of NH3 will decrease.
hey?
The yield of NH3 will decrease.
The yield of NH3 decreases, yeah. So use the question for your guidance. So if the question asks you about equilibrium yield, what happens to the equilibrium yield of ammonia when the temperature increases? And you answer, well, it shifts the equilibrium position to the left. You haven't answered the question. Questions about yield, you've got to answer about yield. Yield goes up or down or stays the same. So make sure you answer the question. You use that as your guidance for what to write. So in this case, we'd say shifts the equilibrium position to the left, or it decreases the yield of ammonia because two more marks to go.
Minimize the change.
Again, don't write minimize the change. If you look at the mark scheme, it'll specifically say ignore minimize the change. Shifts to the left because
Oh,
Negative.
because well, is this for increasing?
we're increasing the temperature of the Haber process.
So
So we're saying it shifts, the equilibrium shifts to the left because,
Because the backwards reaction is endothermic.
right. Reverse or the backwards reaction is endothermic. You must get that in somewhere. Oops, I'm not going to put that in brackets. In fact, I'll probably start with that. Reverse reaction's endothermic, so the equilibrium position shifts to the left to,
Minimize.
don't say minimize the change, but think it and then say, okay, what's the change and how is it being minimized?
Temperature minimized by
Reduce the,
yield.
well, if you're increasing temperature, it's trying to absorb the energy.
okay, to absorb the extra
Absorb
energy
the
would be a
extra
really good
energy.
answer. I was just going to say to reduce the increased temperature. All right.
Because endothermic reaction.
That's your Le Chatelier statement, and it must be there for you to get full marks. You must talk about Le Chatelier's principle but please don't trot out minimise the change as if it's some sort of magic mantra which will always gain you marks. It won't. You need to apply it to the situation you've been given in the question and answer that. So if we're increasing pressure, then we'll talk about to reduce the added pressure, or to absorb the extra energy, or to use up the extra reactant, or whatever it is. Okay. Quick reminder about pressure. Again, the guiding principle, I didn't actually write this down, shift the equilibrium position in the endothermic direction is always true for an increase in temperature. That's your guiding principle. What's the guiding principle for pressure? Shifts the equilibrium in?
The side with the least amount of moles.
Shifts the equilibrium.
It's for increase there.
To the, oh yeah, increase, thank you. An increase. Shifts the equilibrium to the side with fewer moles of gas, of course, but you'll never be given an equation with gas, liquid or solid in. It'll always be all gas or all solution. So increase in pressure always shifts the equilibrium to the side with fewer moles of gas, which of course for harbour is to the right. You're just looking at the balancing numbers 1, 3 and 2. So 1 and 3 makes 4 on the left and 2 makes 2. So the equilibrium shifts to the right to absorb the extra pressure or to reduce the extra pressure, which of course is a good thing because that'll increase the equilibrium yield of ammonia, which is what we want to make. Literally just taught this to year 11s. So it's all the same as year 11 stuff, hasn't changed. Year 11 separates, that is.
What's KC?
Yeah, Casey, let's do that now. Good old Casey. That's a good egg. I've got a better reaction to KC. W, I don't want to do W, X and Y. There we go, that's better. So KC is how would we sort of describe it?
The equilibrium constant.
It's the equilibrium constant. Very good.
It's
How would I work it out?
well, you do NO squared.
No, that's at the bottom.
No, NO squared is right.
Yeah.
Yeah. So products on the top. Yeah, that's the first thing to remember. Products on the top. How do we show concentration of? Square brackets, and it's raised to the power of
Well,
balancing numbers. Yeah. So NO, square brackets around NO, and then because it's 2NO, it's NO squared, and multiply that by O2, and then NO2 squared would be on the bottom. How do we work out units for KC?
it's the volumes.
With the little equations,
Of the well, the concentrations. Well, the volumes. Right. The concentrations should cancel out if it's equal.
Those concentrations won't. Well, some of them will
Well,
cancel.
some of them, but those don't.
Yeah. So if we
You can't do the squares.
if we replace those symbols with units,
Cancel this out.
so we'll have mole per dm cubed squared times mole per dm cubed over mole per dm cubed squared.
Cancel this out, the square bit. It's more DM.
And then we'll cancel. So we'd just be left with mole per dm cubed on the top. But every example is going to be different. You'll have to work it out specifically for each KC. All right, let's just use this.
We'll table, put a table on.
Yeah, we'll get to the table. So I've got 21.3 grams of nitrogen dioxide heated to a constant temperature in a flask. I've got a volume of 11.5 dm cubed. So let's put this down here. Initially, 21.3 grams of NO2, and then at equilibrium we had 7.04 grams of oxygen. So what's our general method for working this out? Ice table.
Yes, totally. That was.
Ice stands for initial, change, and equilibrium. So our initial amount of NO2 is 21.3, well that's a mass, grams. So
That's your initial.
what do I do first? Hey?
21.3
Is,
NO2.
that's mass though.
Find the moles.
Find the moles, yes, thank you. How do I find the moles? Divide by formula mass. So moles of NO2 is 21.3 over 46. 4, 6, 3. What else do I know?
Equilibrium for oxygen.
Equilibrium value for oxygen.
Yeah, 7.04 divided by 32.
Yep, 32 for O2.
0.22.
Where does that go on my ice table?
So equilibrium and oxygen.
Equilibrium for oxygen, so down there. Now what can we fill in? Go on.
Oh no, I was going to ask a separate question.
Ask a separate question.
You know, if it's a data covalent bond and you draw an arrow, is it pointing from which, like the bond?
It's pointing from the lone pair. It's the lone pair that's being donated to the. Yeah. What else can I fill in on my ice table?
What's your zeros on the reactor?
I can put zeros up there. We didn't start off with any
0.44
reactants.
for 2 NO2.
So 2 NO2. So if I put that in the change line there, if that's gone up by 0.22, then this must have gone down by
0.44.
0.44, and this must have gone up by
0.44. And then 0.23. Easy.
okay. So remember the all-important line, the change line, is in the same ratios, ignoring pluses and minuses. The change line's in the same ratios as the balancing numbers. So 2 to 2 to 1, 2 to 2 to 1. Before I start feeding numbers into KC, I need to remember to divide by the volume. So KC is NO squared, so 0.44 over 11.5 squared times 0.22 over 11.5 times 0.023, sorry, divided by 0.023 over 11.5, all squared. So lots of places to trip up on your calculation there. Forgetting to divide by volume is pretty common. And that comes up to a nice round old 7. Okay, that's the worked example from the Kinetics and Equilibria workbook there. Okay, so Don't forget your ice table. We get a lot of people who get it wrong because they think, oh, I don't need an ice table for this one. It's nice and easy. Don't forget your products on top. Raised to the powers of the balancing numbers. And yeah. Don't forget units is different for every single KC. You need to work it out. All right, that was fun. This time I'll hit the stop button.